All right, let's talk about quantum physics. You've probably heard it's weird, right? Well, today we're going to dive headfirst into that weirdness and try to make sense of a world that, honestly, doesn't seem to make any sense at all. I'm going to start with a pretty bold statement. The world you see around you, the solid, predictable world of coffee cups and car keys, it's not the real world. It's more like an illusion, a surface layer. Because underneath all of it, there's a reality that operates by a completely different and, frankly, bizarre set of rules. So, you ready to pull back the curtain? Ready to see what's really going on at the very foundation of everything? Let's do it. Our journey starts with probably the most important, most mind-bending experiment in the history of science. It's called the double-slit experiment, and this is where our common-sense view of reality just completely falls apart. The experiment forces us to ask a question that sounds completely impossible. How can a single, tiny particle, an electron, fired all by itself, end up creating a pattern that looks like it was made by waves interfering with each other? It makes no sense. Let's walk through it. Think of it as a three-act play. In Act 1, we fire little pellets, like tiny bullets, through two slits. What do we get on the screen behind them? Two bands. Simple, predictable, makes sense. Act 2, we send waves, like water waves, through the slits. They spread out, interfere with each other, and create a pattern of many bands on the screen. Again, totally logical. But then comes Act 3. This is where things get crazy. We fire single electrons, one at a time. And what pattern do they make? The wave pattern. It's as if each individual electron went through both slits at the same time and interfered with itself. How is that even possible? To answer that question, we have to introduce the first wild rule of the quantum world. It's a rule that basically rewrites the definition of what it means to be somewhere. And that rule is called superposition. All it really means is that a particle, like our electron, doesn't actually have a definite location until we measure it. Before that, it exists in a kind of ghostly blur of all its possible locations at once. It's not here or there, it's here and there, and a little bit of everywhere else, all at the same time. So, what's the answer to our puzzle? The electron doesn't choose a slit. It exists as a wave of probability, and this wave goes through both slits simultaneously. Then it interferes with itself on the other side. Yep, it's in two places at once. Okay. But what if we try to catch it in the act? What if we put a little detector right by the slits to see which one the electron actually goes through? Surely that will solve it, right? Well, this is where it gets even weirder. This is the famous observer effect. When we're not looking, the electron is this ghostly wave of possibility, creating that interference pattern. But the second we place a detector there to observe it, bam! The wave pattern vanishes. We just get two simple bands, like we were firing bullets all along. It's as if the electron knows it's being watched, and the very act of measuring forces it to pick a side and behave like a good, solid particle. So, if you're thinking your brain is already melting a little bit, just hang on, because what we're about to discuss takes the weirdness to a whole new cosmic level. We need to talk about quantum entanglement. Okay, so what is entanglement? Imagine two particles become linked in such a profound way that from that moment on, they are essentially a single system. They share the same existence. The crazy part is, this connection holds true no matter how far apart they are, whether they are a millimeter apart or on opposite sides of the galaxy. What happens to one instantly affects the other. Now, to see why this is so strange, let's use an analogy. Imagine I have a pair of gloves. I put the left glove in one box and the right glove in another. I shuffle them and send one box to you on the other side of the planet. When you open your box and see a left glove, you instantly know I have the right one. But here's the key. That information wasn't created when you opened the box. The glove was always a left glove. You just discovered a fact that already existed. That is not how it works in the quantum world. Entangled particles don't have definite properties like spin until you measure them. They're in a state of pure, undefined potential. The very instant you measure one particle, forcing it to choose a spin, say, up, its partner, no matter how far away, instantly chooses the opposite spin, down. It's not that you discovered a hidden property. The property itself was created at the moment of measurement, across any distance, instantly. Now, this idea of an instantaneous, faster-than-light connection, while it deeply, deeply bothered one person in particular, Albert Einstein. To him, This wasn't some cool feature of the universe. It was a sign that the theory of quantum mechanics had to be missing something. He famously called it spooky action at a distance. Einstein just couldn't accept it. He argued there must be some hidden variables, like secret instructions that the particles carried with them from the start. He was convinced that quantum mechanics was just an incomplete theory.
Einstein's view has a name, local realism, and it's based on two ideas that just feel like common sense. First, locality. Stuff can only be affected by its immediate surroundings, no spooky, faster-than-light influences. Second, realism. Things have definite properties even when we're not looking. That glove is a left glove inside the box, period. This is the universe we think we live in.
For decades, this was just a huge debate, a philosophical argument. But then, in the 1960s, a physicist named John Stuart Bell figured out something incredible. He found a way to turn this philosophical debate into a real physical experiment. His idea, Bell's theorem, was basically a way to put reality itself on trial. Here's the gist of it. Bell showed that if Einstein's common sense view was right, if there were hidden instructions, then the results of thousands of measurements on entangled particles would have to stay below a certain mathematical limit. But if quantum mechanics was right, and reality is truly spooky, then the results would break past that limit. It was a clear-cut test. One theory had to be wrong. And the results are in. For decades, physicists have run this experiment over and over, closing every possible loophole. And every single time, the result is the same. The universe breaks Bell's limit. Quantum mechanics was right. Einstein, one of the greatest minds in history, was wrong about this one. Reality is non-local. That spooky action at a distance, it's real. So, if our universe is fundamentally spooky and interconnected, if things don't exist until we look at them, then what even is reality? This question takes us out of the lab and into the mind-bending world of quantum interpretations. Now, there are a bunch of interpretations, but let's look at the two big ones. First, there's the Copenhagen interpretation. This is the classic view. It says that wave of possibilities is just a mathematical tool, and when we measure something, the wave just mysteriously collapses into the single reality we see. Then there's the many worlds interpretation. It says, no, the wave is real, it never collapses. Instead, every time a measurement could have different outcomes, the entire universe splits into branches, and every single possibility happens in its own parallel universe. So yes, in one universe, you turned left, and in another, a perfect copy of you turned right. And here's the really wild part. Right now, there is absolutely no experiment we can perform to prove which interpretation is the right one. They both predict the exact same results for any experiment we can do in our universe. So choosing between them isn't a matter of science, at least not yet. It's a matter of philosophy. And that leaves us with this incredible, profound question. Is our reality just one outcome that magically pops into existence when we look? Or are we just one branch on an infinitely sprawling tree of parallel worlds? The science can't tell us. So you have to wonder, which reality do you choose to believe in?